Hi everyone, I'm Nick and welcome to the screencast for Lecture 4 of your Respiratory on oxygen. Not surprisingly, when I took a look at the national curriculum, it turns out they expect us to know a fair bit about our favorite element. I apologize in advance, this is a bit of a drier topic, but it is an important one, and we'll try to keep it interesting as we follow the oxygen cascade. So the oxygen cascade is a concept that describes the gradual reduction in the partial pressure of oxygen that occurs in the process of oxygen movement from the atmosphere to its ultimate site of action in the mitochondria. In other words, at each major transition, the partial pressure can only be lower than it was than where the oxygen came from. It's usually divided into four main steps. Step 1, which is the movement of oxygen molecules from the environment into the alveoli. Step 2, the movement of oxygen from the alveolar sacs into the bloodstream. Step 3, the transport of oxygen from the pulmonary capillaries into the systemic capillaries. And step 4, oxygen diffusion from the blood into the cell, and more specifically the mitochondria, for consumption. Step 1, which is ventilation, is covered in other lectures, so we'll skip ahead to step 2 from here. So, as we already know that at the level of the alveoli, the partial pressure of oxygen is lower than it is in the environment. So if we wanted to calculate our expected alveolar PaO2, we can use the alveolar gas equation. If we assume normal breathing, this equation consists of a few components. First, in green, you can see the external environmental pressure at sea level, which is about 760 millimeters of mercury. From this, we subtract the expected partial pressure of water we expect to find in humidified airways, which is usually about 47. And then that number is multiplied by the FiO2 to get the fractional partial pressure of inspired air that is composed of oxygen. However, we also know that the alveoli are having carbon dioxide constantly diffuse into them from pulmonary capillaries. So the last element of the equation is the subtraction of the relative content of CO2 expressed as the arterial CO2 divided by the respiratory quotient, which is itself a ratio of the CO2 produced to the oxygen consumed. When all of these numbers are plugged in, that result is an alveolar PO2 of about 105. By comparison, deoxygenated blood arriving at the pulmonary capillaries has a partial pressure of about 40. This delta P of about 65 millimeters of mercury provides the driving gradient for oxygen diffusion into the bloodstream. The alveolar gas equation becomes clinically relevant when we use it to calculate an AA gradient by comparing the calculated alveolar PaO2 to the measured arterial PaO2. It's normal for there to be a gradient of about 5 to 10 millimeters of mercury due to normal physiologic shunting. However, in the setting of hypoxemia, an elevated AA gradient can help point you towards causes of pathophysiologic shunting, such as ARDS, pneumonia, or pulmonary edema. Now that we've made it into the bloodstream, step 3 is the bulk movement of oxygen from the lungs to the systemic capillaries. Arterial oxygen content is divided into two main compartments. Oxygen bound to iron moieties on hemoglobin, which accounts for about 97% of the total oxygen content, as well as a small amount of freely dissolved oxygen which continues to exert a partial pressure. The oxygen content equation combines these two forms to give you a total calculation of oxygen content in mils of oxygen per deciliter of blood. Relating this to clinical practice, the relevant point here is that an arterial PaO2, which is what we measure in an ABG, really only tells us about that roughly 3% of oxygen in the dissolved form. To get a more complete sense of arterial oxygen content requires us to look at the measured hemoglobin and percent hemoglobin saturation, which also show up at the bottom of an ABG printout. The last point I wanted to make about this is that what we're ultimately interested in is oxygen delivery, or DO2, which you can see here as the first equation from Barash's table. DO2 is simply calculated by multiplying the arterial oxygen content by cardiac output. Thus, in a clinical situation where arterial oxygen content is low, in addition to trying to improve oxygenation, we can also augment cardiac output in order to improve oxygen delivery. In the interest of time, we'll have to gloss over the details of hemoglobin's role in oxygen transport, other than to say, although that we know the measured arterial PO2 is really just measuring dissolved oxygen in blood, there is still a predictable relationship with the percent saturation of hemoglobin under normal physiologic conditions. However, as we can see from this diagram of the oxygen-hemoglobin dissociation curve from Miller, certain factors can cause hemoglobin to have a higher or lower affinity of oxygen, the net result of this being a different hemoglobin saturation for a given arterial PaO2. Alright, we're almost there. On to the last step of the oxygen cascade, or the transport of oxygen from the bloodstream and into the cell for use by mitochondria. Going back to cellular respiration, you will recall that the cell breaks down glucose in a series of reactions in order to generate the energy currency of the subcellular level, ATP. As such, we will now spend the next 35 minutes doing a deep dive into the Krebs cycle and the electron transport chain. Just kidding, but the big picture of this, and the one that relates back to clinical practice, is the difference in the efficiency of this process under aerobic, or oxygen-rich, versus anaerobic, or oxygen-poor conditions. In the absence of oxygen, glucose is broken down to generate 2 molecules of ATP and 2-pyruvate, which are subsequently converted to lactic acid. However, if oxygen is available, it can be harnessed by mitochondria to drive the electron transport chain and oxidative phosphorylation. In more accessible terms, those molecules of pyruvate can instead be further broken down, and the net production of ATP per molecule of glucose jumps to 36. That's almost 20 times as much energy. This massive difference explains why we are so dependent on oxygen to efficiently run the machine of the human body, and why so much of our job as anesthesiologists boils down to just trying to find a way to get it into our cells. That's it, a big picture overview of the oxygen cascade. Thank you for your attention and for bearing with me. The answers to my questions are B, C, consult medicine, and chocolate cake. See you all on Thursday.